All right, so today we are going to be diving into some seriously cool physics.
Definitely.
Like Nobel Prize winning physics.
Absolutely.
We're talking about the quantum Hall effect.
The quantum Hall effect.
I think a lot of people, when they hear that, they're like, what?
Yeah.
Like, what even is that?
It sounds very intimidating.
Yeah.
But it's really not as bad as it sounds.
Yeah, and actually it's super interesting and important, and we're going to break down exactly why.
Yeah.
And we have some excerpts from Klaus von Klitzing's 1985 Nobel lecture to help us with that.
Yeah, and I think what's so fascinating about this is that this really fundamental discovery comes from something that everybody listening probably uses every single day.
Really?
Semiconductors.
Okay.
Which are like the heart of all of our electronics, right? And von Klitzing was really using them as this window into something much deeper.
Yeah, see, when I hear semiconductor, I'm like, okay, computer chip.
Yeah.
Like what's so groundbreaking about that?
Yeah.
So what was he even doing with these semiconductors?
Mm-hmm. So he was working with what are called silicon field effect transistors, or MOSFETs.
MOSFETs.
Which are really like the cutting edge even back then.
No.
And these devices allowed him to create something called a two-dimensional electron gas.
Okay, a two-dimensional gas.
Yeah, a 2DEG.
A 2DEG.
Yeah, you'd like that.
I mean, it sounds cool. I need a little bit more than that.
So you can think about it as electrons that are trapped in a layer so thin that they're almost like stuck on a flat surface.
Okay.
So they can move freely in that plane, but their motion's really restricted in the third dimension.
Okay.
So that's your 2DEG.
So instead of them bouncing around in 3 dimensions like they normally would, they're confined to this very thin layer.
Exactly. And so this is really the platform for the quantum Hall effect.
Okay, so how does a 2DEG lead to the quantum Hall effect?
So this is where things get really interesting.
Okay.
So you take this 2DEG, right, and von Klitzing applied a strong magnetic field perpendicular to it. So almost like you're holding a magnet above that flat surface of electrons.
Right.
And whenever you apply a magnetic field, electrons want to move in circles.
Okay.
So they're doing these little orbits, we call them cyclotron orbits.
Uh-oh. Yeah.
Yeah, so we've got our electrons trapped in 2D doing a little dance in a magnetic field.
Right, so then what happens?
So you'd think, right, if you're changing the strength of this magnetic field, that the resistance of this two-dimensional electron gas would just change smoothly with it, right? Like it would just kind of you crank up the magnetic field and the resistance would go up smoothly or down smoothly.
Okay, yeah, that makes sense.
But that is not what von Klitzing found.
Oh.
It did not change smoothly.
Oh.
Instead, what he found is that this resistance would get stuck at very specific values, and it would form these plateaus.
Oh.
And these weren't just any random values. They were directly related to these fundamental constants of the universe.
Well, hold on.
Yeah.
Are you saying that this semiconductor, this thing, can tell us about the entire universe?
Yes. It's like finding this hidden message encoded in something that we thought we understood.
Wow.
And it gets even weirder. So you remember how we're talking about measuring the resistance across the 2DEG perpendicular to the current. Yeah. That's the whole resistance, right?
Right.
But there's also a resistance along the direction of the current flow.
Right.
And that's where things get really strange.
Okay, so there's 2 resistances to keep in mind here.
Exactly.
Okay, so what happens to that resistance?
Yeah.
When the Hall resistance gets all stuck on a plateau?
It basically vanishes. It goes to almost zero.
No way.
Yeah.
Wait, so you're saying by applying a magnetic field and then measuring the resistance in a very specific way, you can make resistance practically disappear?
Pretty much. It's really mind-blowing.
How is that even possible?
Yeah, so to explain this, von Klitzing pointed to what are called localized states.
Okay.
So you can think about these as imperfections in the material, little defects that trap some of the electrons and prevent them from contributing to that current flow.
So it's some of the electrons get stuck in these potholes in the material.
Yeah, exactly.
Okay.
And the rest of them can just kind of flow freely with almost no resistance.
That's so weird.
Yeah, it's you've sidelined some of the electrons.
Right.
And now the rest of them can move in this super organized way with no resistance.
Okay, that's wild. But why does the Hall resistance specifically become like quantized.
Right.
Like, what's so special about those plateaus?
So this is where like the true like beauty of this effect really comes in.
Okay.
So this precise quantization that we're talking about, it comes from the fact that the electrons in this 2D EG, they can only exist at very specific energy levels when they're in a magnetic field. So you can kind of picture it like the electrons are climbing a staircase.
Okay.
And they can only stand on the steps, right? It can't be in between the steps.
Okay.
And so those steps, those are the quantized energy levels.
Okay, so the steps are like the quantized energy level.
Exactly. And they're called Landau levels.
Landau levels, okay.
Yeah. And as you change the magnetic field, the space between those steps changes. And so when a Landau level is completely filled with electrons, that's when you get a plateau in the Hall resistance.
Okay. So the filled Landau levels are what's important for this quantization.
Exactly.
Okay. And then those localized states, those like potholes that we were talking about, they play a role too.
Yeah. So think about it this way.
Okay.
As you change the magnetic field, you're changing how many electrons are getting trapped in those localized states.
Okay.
But the filled Landau levels, those are unaffected.
Okay.
So those are what determine this precise quantization.
So it's like the filled Landau levels are like the foundation.
Exactly.
That's like very stable.
Yeah.
And then the localized states are kind of like changing around that.
Yeah, it's like fine-tuning around that.
Okay. This is all starting to make sense now, but like why is this a big deal?
Right.
Like why should we care about the quantum Hall effect?
So for one thing, it totally revolutionized our understanding of how electrons behave in solids.
Okay.
But even beyond that, it has these like really profound implications for like physics as a whole.
Okay. Like what?
Like the big picture here is that the precision of those plateaus allows us to measure these fundamental constants of the universe with incredible accuracy.
Wait, so you're telling me we can learn about the fundamental, like, laws of physics from looking at electrons trapped in a semiconductor?
Pretty much. It's kind of crazy when you think about it, right?
Insane.
Yeah, it's like this unexpected connection between the microscopic world and these, like, fundamental constants of the universe.
So we can use this, like, this effect to, like, test our understanding of physics.
Yeah.
And like make sure like what we think are the laws of physics are actually correct.
Exactly.
That's incredible.
It's like a really powerful tool.
Yeah. You said it also had like practical applications.
Yeah, absolutely.
What are those?
So it's actually really important in the field of metrology.
Metrology.
Which is basically the science of measurement.
Okay.
How we measure things.
Right.
And this is because it provides us with a really, really precise way to create resistance standards, which are like, you need those if you're going to calibrate instruments and make sure that things are accurate.
Right. So like all the instruments that we use for science have to be like calibrated in the same way.
Exactly.
So that's what this effect is useful for.
Yeah, you can kind of think of it like having a perfect ruler.
Okay.
That never changes, that you can use to compare everything to.
Okay. Wow. So we went from like electrons in this thin layer to like completely changing how we measure resistance.
Yeah. And what's really amazing about this is von Klitzing wasn't even setting out to do that.
Really?
He was just exploring this like really cool phenomenon.
Wow.
And it led to this like huge breakthrough.
So it's like all about just like looking at the universe.
Yeah.
And just being like curious about how it works.
Exactly.
That's amazing. Well, we've gone on a wild ride today.
It's definitely.
Talking all about the quantum Hall effect.
It's pretty mind-blowing.
It really is. So hopefully, to our listener, you're leaving with a little bit more knowledge than you came with and a better appreciation, I think, for just how interconnected everything in the universe is.
Absolutely.
And how important scientific exploration is.
Couldn't have said it better myself.
Until next time.